Hello and welcome to the Daily Space for today, December 15th, 2020. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Today we are going to be joined by guest Dan Biermann, who has advanced the story of water on Mars with a new paper describing subsurface water ice that was revealed with radar data. Before we get to the interview, however, we have a wealth of news to cover that takes us from the beginning of the universe to space weather taking place right now. In case you missed it, yesterday was Chaos Day in astronomy. In rapid succession, we had a solar eclipse, we had the Geminid meteor shower, and the Hayabusa team opened up one of their samples and they found that sample chamber A contained a nice quantity of black grains and chunks from the asteroid Ryugu. While all these events took place, science also rolled on with one of the weirdest new papers taking a look at a 11 Jupiter mass planet in a wild orbit around a binary system. The two central stars are both hotter and larger than our sun, and they are in a tight orbit such that they appear as a single star unless looked at spectroscopically. Surrounding the stars is a massive debris disk that caught astronomers' eyes and, starting in 2005, caught their telescope time as well. During a multi-year study, a faint speck was seen to co-move with the stars, leading a team led by Vanessa Bailey to publish the discovery of a planet in a several hundred astronomical unit orbit. This world is orbiting several hundred times Earth's distance from the sun away from its two stars. Now, with an even longer observing baseline, and the combined efforts of Hubble and several ground-based telescopes, this world has been charted to have an elliptical orbit that is highly inclined relative to the debris disk. And that orbit is actually stirring up the debris disk with every passage around the twin suns. According to team member Robert DeRosa, the idea is that every time the planet comes to its closest approach to the binary star, it stirs up the material in the disk. So every time the planet comes through, it truncates the disk and pushes it up on one side. This scenario has been tested with simulations of this system with the planet on a similar orbit. This was before we knew what the orbit was, he says. We've never seen a planet in this kind of an orbit before. This is largely because our planetary searches aren't sensitive to this kind of a world, so we really have no idea how common this kind of a planet might be. It could be very common, as we think our system may have a ninth planet on its distant reaches out in the distant reaches of the solar system, with an orbit not too different from what we're seeing here. In both cases, an encounter with two massive objects may be the reason for their weirdness. In the case of HD 106906b, the migration was driven by the stars. According to a NASA press release, the prevailing theory is that it formed much closer to its stars, about 3 times the distance that Earth is from the Sun. But drag within the system's gas disk caused the planet's orbit to decay, forcing it to migrate inwards towards its stellar pair. The gravitational effects from the whirling twin stars then kicked it out onto an eccentric orbit that almost threw it out of the system and into the void of interstellar space. Then, a passing star from outside the system stabilized the exoplanet's orbit, and it prevented it from leaving its home system. For our own Planet 9, interactions with Jupiter and Saturn may be to blame, but it's really hard to say until we find it. So far, no other exoplanets have been found orbiting HD 106906b. The star system is about 15 million years old, which is kind of a baby, and other worlds are possible. When or if the JWST is able to launch, this system is a prime candidate for its infrared observing powers that would be able to detect other worlds the size of Saturn or larger. For now, our current understanding of this system is summarized in a paper in the Astronomical Journal with first author Meiji Wing.
Back here, closer to Earth, we take a look at water on Mars. Now, water on Mars is nothing new. We know there are briny subsurface reservoirs on Mars. Earlier this year, 3 such lakes were found. In a new paper in the journal Icarus with lead author Dan Berman from our own Planetary Science Institute, researchers detail the finding of another large reservoir, this one of water ice. Using data from the Shallow Radar Instrument aboard NASA's Mars Reconnaissance Orbiter, the team mapped what are called viscous flow features, which are ice-rich flow features in the southern hemisphere of Mars. These features showed a dense concentration in Nereidum Montes along the northern rim of the Argyre Basin. Yes, I had to figure out all of those words. Located in this subregion are a large number of ice-rich deposits, the paper says, potentially the largest concentrations of any non-polar region in the southern hemisphere. Further analysis shows that the deposit is almost entirely water ice. Berman explains, our radar analysis shows that at least one of these features is about 500 meters thick and nearly 100% ice, with a debris covering at most 10 meters thick. This region would be an interesting landing site due to the large amounts of ice, which could be used as a source of water. Unfortunately, it is very mountainous terrain, and it would be likely difficult to land there. Still, it's good to know these regions exist on Mars. As Pamela and I say, where you find one, you usually find more. And of course, we'll have Dr. Berman on after the news to talk about this discovery. Stay tuned for more stories. We'll be back after a short ad break.
So this is a new experiment. This will look better next time. We are gearing up to accept sponsorships here at CosmoQuest. And since we don't currently have any sponsors, I'd like to remind everyone that we have a Redbubble store. If you, like me, are Team Series, we've got a shirt for you. You can help us remind everyone that, well, Ceres is the OG former planet. Go get your shirt today at redbubble.com/people/CosmoQuestX/shop, which is an awkward URL. So if you'd like something a little less awkward, well, there's a QR code. Anyways, thank you. Check it out. Christmas is coming. Okay, now on to the next story. Awkwardly. Welcome back. When I was in grad school, there were a lot of things we learned as the universe is doing either this thing or that other thing, so though the universe had to be limited in its options. One of those things was galaxy formation, which was described as either bottom up or top down, meaning either they formed through the merger of a lot of tiny systems or through the collapse of a massive cloud of gas and dust to go from zero to a fully formed galaxy like Athena bursting fully formed from Zeus's head. We know at least our galaxy formed hierarchically through the buildup of small systems into the larger barred spiral we enjoy today. Other systems we keep finding do actually take another path. The observations taken of the elliptical galaxy C1-23152 show that this distant elliptical galaxy seems to have been formed by the time the universe was just 1.8 billion years old. Data from the Large Binocular Telescope highlights massive amounts of star formation that took place during the galaxy's first 500 million years, leaving it to evolve as a red dead system not too different from the elliptical galaxies we see in our modern universe. This work is published in the Astrophysical Journal with first author Paolo Soraso. According to co-author Francesco Libera, the observations show that the formation of the most massive galaxies in the universe can occur extremely quickly through an extremely intense star formation process in the early universe, as for C1-23152. Co-author Adriana Gargello goes on to add, understanding whether the scenario that describes the formation of C1-23152 is a particular case or whether, on the contrary, it is what happens for most of the most massive galaxies in the universe, It's fundamental. Um, it's of importance since what would require a profound, sorry, I'm going to start that sentence over. It is what happens for most of the most massive galaxies in the universe, and it is fundamental of importance since this would require a profound revision of the galaxy formation models. Once again, the universe is trying to tell us it's not a either or, it is an and.
Keeping with my usual planetary science theme, I take you now to Jupiter, where scientists have been using data from the NASA's Juno spacecraft to solve mysteries left from analysis of Galileo data taken 25 years ago. Think about how you imagine Jupiter from the images we have. Cloudy, dense, gassy, so unlike Earth, it's honestly hard to imagine. The Galileo mission sent a probe into Jupiter to try and understand just how different the giant planet is. And the results were so surprising that they thought it was an anomaly. Basically, they thought the probe had gone into a hotspot, something as uncommon on Jupiter as it is here on Earth. It turns out, though, that what they thought was a patch of hot, dense gas, localized atmospheric deserts that traverse the northern equatorial region, is actually just how the entire northern equatorial belt is. Per the press release, the implication is that the hotspots may not be isolated deserts, but rather windows into a vast region in Jupiter's atmosphere that may be hotter and drier than other areas. Juno's high-resolution data shows that these Jovian hotspots are associated with breaks in the planet's cloud deck, providing a glimpse into Jupiter's deep atmosphere. This dry atmosphere may also be the cause of the shallow lightning and mush balls reported on earlier this year. Tristan Guyot, a Juno co-investigator, explains, high up in the atmosphere where shallow lightning is seen, water and ammonia are combined and become invisible to Juno's microwave instrument. This is where a special kind of hailstone that we call mush balls are forming. These mush balls get heavy and fall deep into the atmosphere, creating a large region that is depleted of both ammonia and water. Once the mush balls melt and evaporate, the ammonia and water change back to a gaseous state and are visible to Juno again. So, Jupiter's atmosphere is drier and hotter than previously thought, and we still have so much more to learn and understand.
I would like to apologize for the chaos that occurred while Beth was speaking. Um, there are going to be some production screw ups today. I apologize. We're trying some new things and they don't always go well. But the news is awesome. So I'm going to continue talking about the news. While Beth has been talking about planets in our solar system, I find myself returning again to discussing exoplanets, specifically exoplanets that may orbit the closest star to our Sun, Proxima Centauri. In a new study of this star using radio telescopes, astronomers have realized that this red dwarf star is even more violent than previously thought. This has consequences for the 2 or more possible planets that orbit in this system. This work was led by Andrew Zwick, who was able to link optical flares from Proxima Centauri with radio bursts. This linkage had been previously seen with our Sun. According to Zwick, our own Sun regularly emits hot clouds of ionized particles during what we call coronal mass ejections. But given the Sun is much hotter than Proxima Centauri and other red dwarf stars, our habitable zone is far from the Sun's surface, meaning the Earth is a relatively long way from these events. Mercury is not someplace you want to be when the Sun acts out, but with Proxima Centauri, even Mercury's orbit is too big to keep it within the habitable zone. The terrestrial world orbiting Proxima Centauri is just 0.05 astronomical units from the star, and its orbit is just 11.2 days long. At this distance, Zwick says, this is probably bad news on the space weather front. It seems likely that the galaxy's most common stars, red dwarfs, won't be great places to find life as we know it. So, if you are working on some great fiction describing a civilization just 4.2 light years away, know that your fiction needs life that is down with being radiated and okay with experiencing all the nasty weather that comes with being a tidally locked world. While life may find a way, it likely won't be something we have so far anticipated.
We talk a lot about habitability here on Daily Space, between exoplanets and icy moons in our own solar system. Of late, we've been particularly focused on Europa and Enceladus. And if you've been watching our Minecraft Monday show, you know I've been a little hyped about Ganymede. With all this excitement about moons of Jupiter and Saturn, it seems some scientists didn't like that Uranus and Neptune's moons were left out of the fun. Being presented today at the AGU's fall meeting, Benjamin Weiss, a planetary scientist at the Massachusetts Institute of Technology, looked at images from Voyager of several of Uranus's moons. Per the article, those images revealed that the moons are made of a roughly 50-50 combination of rock and ices, and like most planetary satellites, have many craters. However, the moon's surfaces also display some of the classic signs of cryovolcanism, like fresh, uncratered material and ridges, valleys, and folds. Using the same techniques that led us to realize that both Europa and Callisto, another of Jupiter's Galilean moons, have subsurface oceans, the team calculated the possible strength of a magnetic field induced by Uranus on its moons. The story goes on to explain. As a moon orbits a planet, it also travels through the planet's magnetic field, which isn't the same strength of direction everywhere. The moon feels a changing magnetic field, which is a process that generates an electric current. How does that lead us to water? Well, water carries electric currents quite easily, and if the moon has water, and that water is carrying the current, it induces its own smaller magnetic field. That smaller magnetic field could theoretically be detected by a magnetometer on a spacecraft near the moons. The calculations from the team showed that a subsurface ocean on Miranda, Ariel, Umbriel, and Titania would be well within the measurement capabilities of current spacecraft technology, although Oberon's field might be right on the edge of detectability. Once again, I beg the powers that be to fund an orbiter to Uranus, please. And now, we'll take a quick break while we bring on Dr. Berman. Stay tuned.
And now for your commercial break. Before we go to rockets, we have a Patreon. This is how we fund everything. Mostly I just want to show you rockets though. Today is a proof of concept. Here are the rockets. Hello and welcome back, everyone. Joining me now is researcher Dan Biermann from the Planetary Science Institute. So Dan, we gave highlights on your new story earlier. Was there anything that we said that was incorrect?
Basically, you got it right. I can clarify that basically what we're talking about here is glaciers on Mars. There are debris covered glaciers all over the planet, um, particularly on the poles, but in the mid latitude regions in the north and south, there are certain regions where there's a lot of them. And this region in particular is around the Argyre Basin, which is one of the largest basins on Mars. It's a mountainous, there's a mountainous ring around the basin. And on the sides of the mountains, I discovered a lot of glaciers that people hadn't recognized before without the newest high resolution imagery. And we used radar data from the Charon instrument on MRO to analyze some of these features. And on one of them in particular, we got a clear signal that they're made of pure water ice underneath that debris cover.
So that's just one of these absolutely amazing things, and I'm sure many of the members of our audience are out there going, "Wait, how did we not notice this before?" Because here on Earth, our glaciers are these mostly shiny, bright things hanging out on the sides of mountains for all to see. How do you end up with a hidden glacier?
Well, they're relatively small, and the you need a powerful enough camera to see them. So our previous images from the Viking spacecraft were too low resolution, and in recent years we've mapped more and more of the planet with higher resolution imagery, particularly the context camera on the Mars Reconnaissance Orbiter, the CTX camera, which is about 5 to 6 meters per pixel in resolution. And with that imagery being almost complete over the planet now, we can really map the surface where these features are. And lo and behold, there's a lot more than we thought.
Now, these glaciers aren't the shiny white exposed to the air that we have on Earth, however. These
Right.
these are covered pretty completely in a layer of dust.
Yeah. The atmosphere and temperature, the temperature and pressure of the atmosphere on Mars is so low that exposed ice pretty rapidly sublimates into vapor on the surface. So it has to be covered with this layer of debris. It's dust and rocks and sand mixed with a little bit of ice on the surface. But these features can still flow down the slopes over millions of years.
So these are in a way not too different from the extremely pollution covered snowbanks that, well, our normal producer Ali is going to be seeing later today, where the snowstorms are hitting on the East Coast. Um, it's just really, really dirty snow, essentially.
Basically on the surface, but underneath that layer, pure ice. And that's what we determine with our radar analysis.
So how does radar allow us to understand the composition of something?
Radar is an excellent tool because it can penetrate the surface, right? And so we get a signal back, it bounces back to the spacecraft, and we measure the time it takes. And when it goes through a material, the properties, the dielectric properties of that material bend the signal. And if we measure that, we can determine what it's made of. So, for example, it goes through the glacier and it hits the base and bounces back, but it comes back at an angle because it's been bent. And if we correct for the dielectric property of ice, it completely flattens it out. So that's how we know it's ice.
And so this is very similar to looking at how light passing through either glass or quartz or some sort of substance here on Earth, how it gets bent tells us what that substance is, and we take advantage of that when we make glasses and prisms and things. You're essentially
Absolutely.
turning this around and just using a very different color of light to
Mhm.
probe Mars.
Basically, yeah. And that was just one aspect of the study, which is really exciting because we were able to confirm that it's water ice. We also used a technique called crater counting to see how old these features are. When did they form? And that allowed us to try to figure out how they formed,
Mm-hmm.
which is, I found really interesting. They're only a few million years old, which is really young for a Mars feature. And over the past decade or so, we've realized that although there isn't much snow falling on Mars right now, uh, in that period several million years ago, the obliquity of Mars, the axial tilt, was much higher, and ice sublimated off of the poles and got redistributed on the mid-latitude regions as snow. And this snow piled up and formed these glaciers.
So these glaciers are in some ways a echo of where the poles of Mars used to be.
Yeah, the where the water was basically, and it tells us about the climate conditions at those times, as well as the tilt of the planet.
And this is one of those reminders of why it's so good that we have the Earth's moon. Our own moon prevents our planet from wobbling about its axis the way Mars wobbles about its axis.
Mm-hmm.
And we don't need to worry about this happening here, but this presents some really cool potential for exploration. You don't necessarily want to send a spacecraft to the Mars poles because there's not a whole lot of sunlight there. But with this echoed ice from the past alignment of the world, we now
Mm-hmm.
have water that is vaguely reachable at a better latitude.
Yeah, traditionally landers are more equatorward, but
Yeah.
I'm sure in the future they'll be able to migrate to these slightly higher latitudes. Although this region that I studied, like I said, it's very mountainous
Yes.
and it might be pretty hard to reach, but you never know.
And you never know if you're going to be roving there or flying there with all of the advances in helicopter technology and
Hmm.
Starship. It could be a hop, a leap, and a skip rather than a rove, rove, rove.
Yeah, very possible.
Now, this research is the kind of thing that builds systematically on so many different ideas. The periodic march of science towards, yes, there is a lot of water on Mars.
Hmm.
Where do you go next with this research?
Well, one of the things that I want to do is to actually calculate the volume of these features, and just do what I did, but on more features because they're all over the place and there's a lot to be studied. We want to quantify what we call the ice budget on Mars, which is basically how much ice is there now and how much is available in the atmosphere and the poles, you know, in the entire cycle of water transfer, freezing, and evaporating throughout Martian history.
Now, one of the more unfortunate things that we find ourselves doing with Earth science is calculating how much more of the world will be covered with oceans if we have significant ice loss. Can you do similar research with Mars where you imagine what the world would be like with all those subsurface glaciers melted, those poles melted, and figure out how much water it would have?
Sure. Yeah, that's pretty easy to do. If we have a volume calculation, we can easily convert that to liquid in a simulation and determine how deep an ocean you would have on the planet. That would make an interesting study as well. They've done that for past Martian conditions. We think
Right.
there may have been an ocean billions of years ago,
Yes.
early in Mars's history, and that's something we're probing as well. That's more ancient Mars history, where I'm looking at more recent Mars history. But Yeah, it's unlikely that would ever happen because Mars is getting colder and drier, not the opposite. But in millions of years, there will be another axial tilt episode. So
So we may see more migration of where the ice is on Mars.
absolutely. Well, we won't see it because it's in millions of years, but we
Well,
can simulate.
humanity will hopefully see it. You can never count
Yeah.
too solidly
Unless
on
they
these things.
unless they engineer the planet and terraform it to be more habitable. But
And
I don't speculate about that.
yeah, and as we've often discussed here, that's probably not a good idea because there is no magnetic field, and whatever work you did to terraform Mars would be undone by the sun.
Radiation, yeah.
Yeah. This is really cool research, and unfortunately, as you pointed out, we keep sending our rovers to equatorial regions where this kind of stuff just can't be drilled into. Um, are there any future plans that you know of for spacecraft that may be able to go out and drill not necessarily into this mountainous location, but into other icy locations?
Not that I know of, although they did have the Phoenix lander, if you recall. How long ago was that? 20 years?
That
15 years?
it was more like 15 years. That was back
Yeah,
in, I believe,
that would
2008.
that was much more in the low polar region, and they drilled through ice and they found some ice, so that was really cool. I'm not aware of any current plans right now, but you never
There's
know.
there's so many places that we wish to explore, from needing to go to Venus to wanting to go to Uranus, and then of course our ongoing exploration of Mars. It seems like there will never be enough budget, but there will always be more things to wish to go see.
Absolutely.
Now, do you have any closing words, anything you particularly want our audience to know about this research that you've been doing?
Well, I think I covered just about everything. I really want to keep studying these features and explore um, how they formed and how they evolved through time. That's the main area of focus for me lately.
That is awesome. So, thank you so much for being with us, Dan. And this has been a really cool interview. Now, before we go, I'm going to give you a few reminders. While the peak of the Geminids has already happened, the shower lasts another few days, and the Jupiter-Saturn conjunction is getting closer and closer. So please, if you have clear skies out there, people, take a moment and look up. Also, our first book club pick, Packing for Mars by Mary Roach, will be reviewed and discussed in the first week of January. Annie has already finished it, and Beth is waiting for her copy at the library. So we're now going to bring Beth back, and Dan, I'm going to bid adieu to you. So pardon me for just one moment while I switch screens to black one.
All right. Oh, it's a Monday on a Tuesday. So anyway, we're gonna do our book club at the beginning. We're gonna do the discussion the beginning of next year. So I'm gonna get my copy and finish it. We're gonna have the discussion on January 8th. That's a Friday. So we'll be doing our book club review that day. We'd like to discuss it on Discord. So if you're in Discord, please come join us for that discussion. Speaking of next year, what? This year that shall not be named is almost over, and we're working to budget for next year. We need your help. I know Pamela is kind of tired of asking, so I'm going to do it this time. Our goal is to sign up 60 new Patreon members by the end of this month, and we are halfway there and halfway through the month. If you are doing okay and you have the financial ability to support us in our science, please consider signing up at patreon.com/CosmoQuestX. This has been The Daily Space.